You know the feeling, right? You're right in the middle of something important, you tap a button on an app, and poof, it just freezes, or maybe it disappears completely. It's super frustrating. But what's actually going on under the hood? Well, today we're going to pull back the curtain on why programs fail and take a look at the really elegant safety net that good software uses to catch itself before it crashes. And to get us started, let's chew on this great quote from Bjarne Stroustrup, who, created the C++ programming language. He says that truly clean code isn't just about being smart or fast. A huge part of it is having a complete, thought-out strategy for handling errors. It's a fundamental part of making something that actually works well in the real world. I mean, of course you have, right? It's something we've all experienced. That abrupt stop, that screen that just vanishes, that's what we're going to dissect today. Because it turns out that moment of failure isn't just a dead end. It's actually a critical point where the program is trying to tell us that something has gone very, very wrong. Okay, so to really get why programs break, you first have to understand that not all errors are the same. They pretty much come in two main flavors. There's the kind that stops a program before it even has a chance to start, and then there's the kind that ambushes it while it's already running. So on one hand, you've got syntax errors. Think of these like a really bad typo in a recipe. Like if it said, bake at 350 degrees with a G. You literally can't even start cooking, right? The whole thing is a non-starter. The program won't run at all. Then, on the other hand, you have exceptions. These are runtime errors. This is more like the recipe is written perfectly, but halfway through, you realize you're out of eggs. The process starts just fine, but then it hits an unexpected problem that forces it to grind to a halt. All right, so let's zoom in on those runtime errors, the exceptions. When a program that's written perfectly fine syntax-wise hits a problem it can't solve, it doesn't just die silently. In a language like Python, it actively and very loudly signals that something has gone terribly wrong. You can almost think of it as a cry for help. And that cry for help has an official name. It's called an exception. Now, here's the key thing to get. An exception isn't the crash itself. No, it's a special object, like a little package of data that represents the error. The program essentially raises this exception, kind of like raising a red flag to say, hey, we've got a problem over here. Now, if there's no code written to catch that flag, that's when the program crashes. And when it does, it usually gives the developer this thing called a traceback. Think of a traceback as Python's detailed incident report. It'll tell you the exact type of error, and it'll even pinpoint the specific line of code that caused the whole mess. It's basically a map leading right to the scene of the crime. So, if programs are bound to run into trouble, how do we stop them from just blowing up and showing that ugly traceback to the user? Well, this is where programmers get smart. They build a safety net. It's a special structure in the code designed to anticipate these problems and say, okay, if this specific thing goes wrong, here's what I want you to do instead. And at the core of this safety net is a really simple two-step process. First, you take any code that you think might be a bit risky and you wrap it in a try block. Then, right after it, you create an except block. This is your backup plan. It tells the program what to do in case that specific error you're worried about actually happens. The except block is the cushion that catches the fall. Let's look at a super classic example, dividing by zero. In math and in programming, you just can't do it. It causes an error every single time. So here, we put that risky division inside the try block. Then we set up a handler, an except block, specifically to catch that zero division error. And instead of crashing, we just tell it to print a friendly message. So let's walk through what happens when this code runs. First, Python enters the try block and starts executing the code inside it, line by line. Everything's going okay so far. But then, bam, it hits the line where it tries to divide by zero. That's an impossible instruction. So Python immediately stops what it's doing and raises a zero division error exception. The normal flow of the program comes to a dead stop. But here's the magic. Instead of crashing the whole program, Python looks for a safety net. It finds our except zero division error block, and control immediately jumps over to it. The code inside that except block runs, the helpful message gets printed, and the crash is completely avoided. It's a really powerful way to turn a total failure into a controlled, predictable response. But hang on, this safety net can get even more sophisticated. That basic try-except structure is just the beginning. We can also add special instructions for what to do when things go right and for cleanup tasks that absolutely have to happen no matter what. First up, we've got the else clause. You can think of this as the success clause. If all the code inside the try block runs perfectly with no errors, no exceptions at all, then and only then the code inside the else block will run. It's kind of like a victory lap for your code when everything goes right. And then there's the finally clause, and this one is so important. The code inside finally is a guarantee. It will run, always. It doesn't matter if the try block worked or if it failed and an except block ran instead, the finally block is the last thing to execute. This makes it perfect for essential cleanup tasks, like closing a file or a database connection, to make sure your program always leaves things neat and tidy. And Python has a whole bunch of these built-in exceptions for common problems. We've already met zero division error. Then there's value error, which happens when you give a function the right type of data but a value that just doesn't make sense, like asking for the square root of a negative number. And of course, the classic name error. That's the one you get when you try to use a variable you forgot to create first. So when you put all of this together, why bother with all this complexity? Why build these try, except, else, finally safety nets? Well, because it fundamentally changes what a program is. It's no longer just something that either works or crashes. It becomes something that can intelligently handle problems as they arise and communicate effectively with its user. This whole idea really matters for a few big reasons. First, it separates your main happy path logic from all the messy error-checking code, which makes your programs way easier to read. Second, it lets your program recover and continue on from a problem instead of just giving up. And maybe most important of all, it transforms an abrupt, confusing crash into a clear, helpful message for the person using the app. And that really brings us to the biggest takeaway from all of this. The mark of truly professional, well-built software isn't that it never runs into errors, because that's just impossible. The mark of great software is that it's designed with the full knowledge that things will go wrong, and it knows how to fail gracefully, predictably, and helpfully. So, I'll leave you with this thought. The next time you're using an app and you make a mistake, maybe you try to type your name into a field that only accepts phone numbers, and instead of just crashing, the app pops up a little message that says, "Hey, please enter numbers only," just take a second. Appreciate what's happening behind the scenes, because you're seeing that invisible safety net, that try-except block, doing its job perfectly.